So I'll go through a glance. So Dodge algorithm, you need to checklist all this version of your software. You need to have Qiskit version 2.1.0 or newer version on IBM Qiskit runtime version 0.40.1 or newer version. Likewise, you need to check each and everything what is. So where to check? How to check? Go to your QBride platform. Go to your QBride platform. So I already shared this link. If you are not able to follow, please go to this link. Once again, I'm sharing today also. So go to this link, create an account using your Gmail or whatever the mail you are using. Okay. So once you logged in, you are able to install all these library packages, okay, related to Qiskit. So once you created the environment, you can launch lab. So lab will look like in this way. Then you can upload your files over here. So this is the upload button. Okay. So I'll share the link also. If you missed yesterday class, you can go to this link. So go to this link, and you can download this notebook. So mention notebook over here. I mentioned notebook over here. So this is where you can find that notebook. Once you click this, yeah, IPUNB file will be get downloaded, and you need to upload over there. Suppose if you missed one or two steps, you are able to achieve it. So click here once you logged in. Click this button, and you can upload whatever the file you download over there. I downloaded Dodge Josha.ipynb file. So once you uploaded, okay, the file will look like this. And here you need to select your kernel. So select here, click here, option will come. So from here you can able to select Qiskit version 2. So if you install Qiskit version, you are able to select like this. So once you selected your kernel, what you can do, you can give select button. Once you selected this kernel, what you're supposed to do, go to kernel, restart kernel, select restart kernel. So once you give restart kernel, okay, your code will appear in this way. So you are able to upload your file, then you need to select your kernel, then you need to restart your kernel. So these are the basic things you need to. So after that, you can go to that file and you can see the cell number 2. Okay. Here you need to uncomment. So previously it will be look like this. Okay. So delete that hash command. Delete that hash symbol. It will appear in this way. Okay. So run this button. So click somewhere in this cell and click run this cell. Otherwise, alternatively, what you can do, you can press Shift plus Enter. I already installed. Once again, I'm doing all these steps. So once you install, what you're supposed to do, you need to restart your kernel. Okay, multiple times you need to restart your kernel before starting your code. So once you started to execute, you cannot refresh. Okay, if you refresh, all the data you will lose forever. Okay. So come to the algorithm part. So in Dodge Josha, what we covered. So we covered this part. So we are giving the input X. So this is our input. Okay. So what is the input? What is the type? It is a binary input type. Either you can provide 0 or you can provide 1. 0 or 1. So this is the logic. Okay. So we are using 4 types of function. This is function 1, this is function 2, this is function 3, this is function 4. Okay. So look at the function 1. Look at the function 1. Function 1 always produce 0. Okay. Function 4 always produce 1. It means these two are constant function. These two are constant function. So look at the function 2 and 3. Look at the function 2 and 3. It produces alternative output. So if you are giving 0 for function 2, for first time it will give 0, for second time it will give 1. Okay. So likewise, this function will contradict the previous output. So this you can see the contradiction. So this is for balanced function. So what type of balanced function? Equally balanced. So you can see. So for the first time you got 0, second time you got 1. For the first time you got 1, the second time you will get 0. It means it is equally balanced. It is equally balanced. So likewise, you are able to understand what this function will do, and you need to identify what type of function you are working with. Okay. So for that, what we are doing, we are writing a oracle. We are writing a oracle. So oracle is nothing but your function. U of f is your function. Okay. So this you can say like oracle, or you can say black box. You don't know what type of function it is. You don't know what type of function it is. Okay. You are giving two inputs. This is your actual input. This is your actual input. This is helper input. Helper input. So sometimes they will call ancilla qubit. Sometimes they will call ancilla qubit. So this will help you to understand your function. Okay, this will help you to understand your function. So there are two types of output you might got over here. So the first one is X. The second one is XOR with, so XOR operation with your function. So what input going to XOR with your function? Whatever you are giving with your Y input. So that is the meaning over here. So this is the generic framework of Dal-Josh algorithm. Okay. So for that, we need to have 4 important steps. Step 1, you need to map classical inputs to a quantum problem. You need to map classical inputs to the quantum problem. So what is our classical input? Binary input. Binary input. So what are the inputs we have? Either 0 or 1. So how to map a quantum problem? We are writing a black box. We are writing a black box and we are giving a quantum input in the term of state 0 and state 1. So this is the primary difference. Okay, your classical input is converted into quantum input for the given problem. Then you need to do step number 2, optimize problem for quantum execution. So we did the first step. We did the first step over here. So what I do, I copy this code. I'll try to put in Notepad++. I try to explain. This will be easier for you. File save as. Always save file with the double quotes. And if you select all types, it will store as it is. So this is a trick where you can save the file as it is in the same form. Okay. So in this code, look at the line number 7. Look at the number 7. What you supposed to do? You need to save your token. So you need to save your account. So line number 8, you need to remove in this way. Line number 8, you need to remove in this way. Remove that hash. And it will give all these options. So channel is IBM Quantum Platform. The instance is your IBM instance CRN, and you need to place your token API key. So these two information you need to copy from your login dashboard. So go to your login, go to your IBM login, go to your IBM login. So this is my login. So once you have valid credit card, then only you are able to create account. So once you created, you can find CRN number over here. So you need to copy this information, just click and it is copied. And in coding over here, you need to replace this part, press delete and paste. So in this way, you need to paste. So I hope everybody able to follow. So first input you need to copy from your CRN instance. Okay, if you click copy symbol, it will get copied. Then you need to paste in this field. So within double quotes. So once you completed, next what you're supposed to do, you need to create API key. So click here, give some name, demo 3. Okay, so you can click create. So it will create some API key. So click that. Okay, and click here once it is created. Click, it is get copied and come to your coding part. Okay, so in case of token, you need to paste this code. You need to paste this code. So this is how you need to place two value. One is instance, one is token. Once you do all these steps, so go back to your coding part. The next line you need to enable in this way. So go to view, enable show line numbers, enable show line numbers. You able to observe over here. Okay, so follow in the same way. So once you have login, so enable line number 8 and line number 9. Observe in your code. Observe in your code. So it will save your account and it will get service from actual quantum computer from IBM. So line number 9, it will get service from IBM quantum platform. So line number 12, okay, it will load your service. It will load your service. So this is for the first time, line number 8 and line number 9 you need to access. So once you saved your credential, it will automatically load. It will automatically load. So line number 16, you need to focus. Line number 16 is about background, a backend. Okay. So backend, what it is mentioned, IBM Brisk Brain. So you can change the quantum computer from your login. So how to do that? So go to your login. Go to your login. Okay. So click here. Click top left. Click top left, and click compute resources. Click compute resources. So if you click compute resources, it will list out what are the quantum computer available for your access. So I have 3 quantum computer, IBM FIS, IBM Markaresh, IBM Torino. So I have 3 quantum computers to access. Okay. So you need to check status. So all these quantum computers are in status. Okay. But I need to select IBM Torino because it is not under maintenance. So remaining first 3, you can observe over here, it is get locked. It means I cannot have access to these quantum systems. So you should be careful while selecting IBM's quantum computer. It should be free, it should be accessible, and should be free from maintenance. It should be free from maintenance. And look over here, pending jobs. So whichever quantum computer is without any pending jobs, you select them. So for convenience, what I did, I selected IBM Torino. For convenience, what I did, I selected IBM Torino. So this contains 133 qubits. So this is the capacity of the quantum computer I can access. So likewise, you need to check from your backend. You need to check from your backend. So here what I supposed to do, I need to select Torino. Same spelling. So you need to double check this spelling, IBM Torino. So once you selected that quantum computer, it will get sampler and it will print the backend. So you need to get output in this way. So here they explicitly mention IBM Brisbane, but in our case, we need to get output like Brisbane, Torino. Okay. So what I do, I'll run this code. I'll run this code. So I got service like IBM Torino, which means it is successful. The attempt is successful. So if you're not able to get this output, it means you have trouble to get real quantum access. Okay. So don't worry if you're not able to get access, you can disable this and you can able to do simulation part. Able to do simulation part. So look at the next part. Look at the next part. Next, we can switch between simulator or real hardware through this part of code. Okay, here you can change. Okay, if you want to use simulator, you can use. I will copy this code. I try to explain. Okay, suppose if you are not able to access the real backend, you are able to load alternative fake backend. So look at line number 8. This is what they mention. This is what they mention. Okay, so what you can do, you can disable this hashtag over here, line number 18 and line number 19, able to do a simulator based sampling. Okay, so multiple ways you can do. Suppose if you are not able to use the real quantum system, you can enable line number 18 and 19. You can try this code. This will, you will get the output over here. Okay, so what is the maximum capacity you are able to do simulation? It is about 18 qubits. So here you can notice. You can do quantum simulation, simulation up to 18 qubits. So first try to run this code, you will get some output. Then after gradually try to increase number of qubits. So my suggestion, if you are able to increase qubit until 30, but if you go 31, 32, it won't support. It won't support. Even if you are using the whole supercomputer, you are not able to simulate beyond 32 qubits. Okay, you will get failure message. You will get failure message. So this we need to keep in our mind. But what is the availability from IBM? They are providing 133 qubits. 133 qubits. So in reality, you cannot simulate 133 qubit using IBM quantum simulation. Okay, simulation has some limitation. A real quantum execution doesn't have these kind of limitations. So this is the primary difference you need to know before doing any quantum experiment. If you keep on increasing your qubits, after some point, you cannot do simulation. After some point, you cannot do simulation. So any doubts in between this? If you don't have real quantum access, please try simulator based. So disable line number 18 and 19 and try to run the code. Is all of you able to run that code? Even you can use the Google Colab to run this code. If anybody doesn't have real quantum access, tell me if you are able to run the code. Put in the chat box. Enable line number 18 and 19. Definitely you will get output. Is it working? Whether it is throwing some error, let me know. Hello, am I audible? Okay, okay, fine. Then we can move to the next part. Next part. So step one, we need to map. We need to map. Step one, we need to map. So line number 3, we are importing quantum circuit from Qiskit library. So line number 5, we are creating quantum circuit. So 2 is your input function. 2 is your input function. So I will zoom sometimes. Okay. So look at line number 8. This is the function definition. So 2-bit underscore function is function name in Python. So within this parentheses, you can see case, integer. So whatever you are giving the value over here, that case will get executed. So it is like switch case. Okay. So if you are giving one, so whenever there is a case 1, it will get executed. So if you are giving 2, it will go for case 2. If you are giving 3, it will go for case 3. Giving 4, it will go for case 4. So likewise, they design this switch case function. Okay. So line number 12, it will check your input type. Suppose if you are giving less than 1 or beyond 4, it will throw a error message. It will throw an error message. So line number 15. So line number 15, it will create quantum circuit function. Okay. It is a function call. So what is the input parameter? You are giving 2. So what is the meaning of 2? It will create 2 quantum bits. It will create 2 quantum bits. So this circuit is named like variable f. So in your circuit, a control knot is implemented. A control knot is implemented if the case is 2 or 3. If the case is 2 or 3. Okay. So look at the line number 17. It will create control knot gate. So if the case is belongs to 3 and 4, what happens? It will create a NOT gate. So this is the function what you have middle of your algorithm. Okay, then it will return that function. So this is how your function is get created. Okay, so here what you can do, you can create a Hadamard gate. You can create a Hadamard gate. Then what you can do, you can create a barrier. Then what you can do, you can call your function and you can give some input for that function. Okay. So finally, measurement is happen across your circuit. Then the circuit is get drawn. Function 2 and 3, it will belongs to balanced function. Function 4, it belongs to constant function. So whatever the function, it is constant, it is able to identify within a single iteration. So that is why we gave 2 chances for balanced function. That is the idea. So identifying constant is very easy. Very good question. Okay. So this is the basic function call. This is the basic function call. So whatever happened over here, we created Hadamard gate. So look at Hadamard gate. So line number 27, we implemented Hadamard gate. That is why we got over here. Maybe I will try to select uh, tool over here. So line number 27, it created a Hadamard gate over here. So line number 28, we created a barrier. We created a barrier. So line number 29, what we do? we call 2-bit function. Okay, by default it will go for the first function. Okay, balance function. So that is why this control not gate is created. Okay, so next what we are doing, we are placing one more barrier. Okay, so this is inside that barrier. Okay, so barrier will created in both ends. So after that, what we are doing? We are doing measurement. So measurement happens over here. So this is a single command. We created both measurements for qubit 0 and qubit 1. So this is how you are able to get your output. You can look for latex, sir. Go to IBM Qiskit, latex output. You need to mention explicitly, then only you are able to create latex output. So this is what we are doing. We are doing MPL. Okay. So if you want to do latex, you need to mention explicitly. I'll share this link to you because you keep on asking. Okay. So this is the way you can showcase in your Jupyter notebook. But if you want to export like an image, you can do in this way. You need to mention file name. So automatically files are get generated. You can create into PDF effect also. I hope it is clear. You can export all your quantum visualization into LaTeX, PDF or JPG or PNG. Okay. So next what we do, we need to do transpile. I'll copy paste this code. I try to execute one by one. So I got IBM Torino. Then what I do, I'll try to get the backend. Then I try to mapping. So this circuit is also executed. Then I need to do transpile. Look at the transpile. Look at line number 2. So here what they mentioned, we try to import a preset pass manager. So it is like compiling. Okay, so if you have a classical program, if you do compilation, that will get converted into a target native language. In same way, you wrote all this Qiskit code in Python. So these circuit need to be converted for actual quantum machine. Okay, so this is for transpilation. Actually, your quantum circuit is converted according to the quantum hardware architecture. Okay, so here it will find its backend. So depends upon your quantum computer line number 4, it will select appropriate architecture. Okay, so here you can generate pass manager according to your desired level. So there are multiple levels available for optimization. So here we chose level number 3, you can select from 0 until 4 or 5. Okay, so this will automatically convert your circuit into actual quantum computer architecture. Then line number 7, what is happening? It will run all your quantum circuit in actual quantum computer. So we completed transpile part. Now we're going to check with step number 3. Step number 3. So step number 3, you can run this quantum algorithm according to your choice. So normally we are mentioning shots 1. It means it will run only one time. So what you can do, you can run for 1024 times also. Okay, because Dodge's algorithm, it need to run only for one time. Okay, for some algorithm, you need to run for multiple times. So you need to know this. For only Dodge Joshua, we are running for single time, because in single time we are able to get the result. But for other algorithm, generally in quantum, you need to run for multiple times. So what is the default value for IBM Qiskit? It will run any given circuit for 1024 times. So note down this answer. So it will help you. It will help you. So for this example, we are running only one time. So this is allocated like a job for your quantum system. This is allocated like a job for your quantum system. So look at line number 5. So once this job is get completed, it will have some result. From that result, we are able to store through this variable. So what we are doing, we try to get only the measured counts from this variable. So multiple measurements are there, but we are focusing only on one data. Okay, so result 0, we able to collect only one quantity. So generally it contains multiple quantity because we are running for multiple times. So line number 4, you look at over here. So line number 4, what we are doing, I try to explain this code. So line number 4, we try to visualize our quantum circuit output. So line number 4, we try to visualize quantum circuit output. For that, we are importing plot histogram. So this is the package which will help you to visualize your quantum visualization. So this is the function called line number 6. Plot histogram is the function called. For that, we are giving counts variable. So refer to the previous code. We already counted. We will already stored results in counts variable. Okay, we try to see what is stored in this count variable through this histogram. And look at your output. Look at your output. So count is 1. So we got 1, 0, 1 for the first iteration. Only single time we executed, right? Single time. So what is the idea of 0, 1? It is a balanced output. So first time we got 0, the second time we got 1. That is why we got 1 as the output. I hope all of you able to run this code. So if you vary your number of shots, you can see multiple outputs. So try to vary your inputs, try to vary number of shots, you're able to see difference between your outputs. So the first problem is Josh problem. We already discussed. We'll go through website because sometimes images not get loaded over here. So this is the circuit diagram of the Josh algorithm, right? So we are preparing 2 qubits, one from state 0, one from state 1. From state 0, we are applying Hadamard. It will go to state positive. So from 0, we are implementing Hadamard, it will go to positive. Okay. From 1, we are implementing Hadamard, it will go to negative. Okay. So here we are noting what is the state which is called phi 1. So this is quantum state. This is quantum state. So we are implementing a function, oracle function. Okay. We don't know what type of function it is, which is called g of f. Then what we are doing, after reacting with this function, again your quantum state will get changed. Again your quantum state will get changed. So you need to trace from backside. You need to trace from backside. So this is the measurement you are doing. Okay. So from measurement, if you are getting 0, it is a constant. From measurement, if you are getting 1, it is balanced. Okay. So for 0, if you are getting 0 from here, binary 0, it means after Hadamard, you need to have stage 0. So it means before Hadamard, what is the gate you are supposed to have? You need to have positive state. So I'll write over here from stage 0, if you apply Hadamard, you will get positive state. From positive state, if you apply Hadamard, you will get stage 0. I try to change color. From state 1, if you apply Hadamard, it will go to negative state. From negative state, if you apply Hadamard, it will go to state 1. Always remember this. So that is why we are tracing from back. This is how we are mapping. Okay. So here we are getting 1. Here we are getting 1. 1 means before measurement, it should be in state 1. So before Hadamard, it should be in minus state. So here how we are mapping our output to the function from the backside. So here you can notice. So what is the output of state 0? Positive state. What is the output of state 1? Negative state in psi 1. Okay. So what is the output of your constant function in psi 2? It is positive. What is the output of balance function? It is negative. So here you need to understand psi 2 to understand the whole operation. Any doubt between these, you can ask me. Is it clear? We can move to next. Please put in the chat box. Are you able to understand? In QBraid, you need to upload that file. In last class, I discussed. You need to upload that file. Okay, here you need to select Biscuit version 2. So before that, you need to install that version environment. So we can vary that function. We can vary different types of function by giving different types of inputs for that function. So that is the exercise given for you. So here you can print what type of function you have. So you can give the number whatever you want. So here you can give 3, here you can give 2, here you can give 1 also. So this is an example for Deutsch algorithm. Okay, so here you can mention from 1 to any option. 1, you can mention 2, you can mention 3, you can mention 4. It is up to you. So try to change your input function so that you can be able to change your function type. Okay. For each and every output, for each and every input, your output varies. For 2 inputs, you will get 0. For 2 inputs, you will get 1. You try to change your input and check your output. So each and every time, it will create different function types. So this is how you need to change your function type. Okay. So I try to change my function type over here. So this is given as 3. Now I am running as 3. So you can see the code automatically generated over here. So if I am giving 3, it will create a control node. If I am giving 3, it will create a control node. So try to create 4. Try to create 4. It will change little bit, right? It will change little bit. So it will create a NOT gate. It will create a NOT gate. So try to change like 2. It will change. So once you created black box, what you can do, you can run, you can run, you can transpile, you can run, then you can visualize your output. So I got balanced output. I got balanced output. Now I try to change the input. Let it make 4, then run. So here you run for twice. So you can see the difference over here. You can vary all these inputs and outputs, and you can check how your function is working. So we come to an extension of Dash algorithm, Dash Josh algorithm. Okay, little difference is there. So in previous case, we have only 2 qubits. So in this case, we have multiple qubits. Okay. So what is the multiple qubits? Multiple qubits can have any value. Okay. So after that, we are implementing a Hadamard gate. So next, we are implementing our Oracle function. Okay. So last qubit, ancilla qubit, starting from 1. So this is always happen. Okay, because we need to identify in a single run. That is why we have difference. So you can see this difference over here. You can see the difference. So all these input qubits starting from state 0. So here it is starting from state 1. So this is differentiable. So if it is differentiable, you are able to run, you are able to identify your output within a single execution. So that is the strength of Dash-Josh algorithm. Okay. So you can notice difference like Dash algorithm, Dash 2 qubits. Okay. Dash-Josha, Dash Josha more than 2 qubits. So this is the primary difference. So it could be 50, it could be 100, it could be million or billion. The process is same. The process is same, but little complicated. Little complicated. So for that, we need to have n plus 1 qubits. I'll copy this code, try to explain. So line number 5 is the function definition. We are defining dash Josha. That is why DJ name is there, dash Josha. And we are creating a random function. So how to create random function, random quantum circuit? So you need to have n plus 1 qubits because n number of qubits starting from state 0 plus 1 for state 1. Okay. So line number 11, it will explain how many random qubits you need to have. So you are starting from 0 to 0, 2. So it will create any value between 0, 2. Okay, it will flip number of output qubits with 50% chance. So it will create X and it will return nothing. So two types of different circuits we are creating. One without doing anything and with a NOT gate. So for an example, for the first time if it is creating 0, the second time it will create 1. So likewise it will create randomly. So that is the difference between a NOT operation. So first time it is created 1, the second time it will create 0. 50-50 chance. So try to understand this code. So it will create randomly. So it will return that circuit. So it will take samples from all the given number of qubits. Okay. So make sure it will do randomly. Half of the inputs are selected randomly for each and every qubits. It will add a control NOT gate. It will add control NOT gate for a reversed bit stream. Okay. So line number 29 to 33, it will add control NOT for your whole circuit. So imagine in that way. So next line number 35 to 39, it will add a multi-control NOT gate. So look at line number 38. Look at line number 38, which stands for MCX. It means multiple control NOT gate. So if you are not familiar with multiple control NOT gate, please go through APSCHE tutorial. They will have ample of materials. I'll show you. I try to show some coding. Okay, wait a second. This is an example for multiple control NOT gate. MCX. Yes, MCX. So I'll share this link to you. Please go through it. So search for MCX. Search for MCX in this web page. So this is multiple control NOT gate. Okay, so Q0, Q1, Q2, Q4 are like control, Q3 is like target. Q3 is like target. So you can look over here. You can look over here. So whatever you mentioned last, it will act like target qubit. So multiple ways you can implement MCX gate. So this is one example. So once it added multiple control NOT gate, we need to mention number of qubits. So we discussed as earlier, Deutsch algorithm only dealing with 2 qubits. If you want to implement Deutsch-Joshua, you need to select more than 2 qubits. So that is why we selected number of qubit equal to 3. Then we are creating an oracle function by using that function. Okay, so this 3 is passed over here. So 3 number of qubits are used for this oracle function, and we try to display. So I try to run this code. I try to run this code as it is. We created a circuit. So if you increase number of qubits, it will automatically select. So instead of 3, if you are giving 4, it will create for 4 qubits. So 4 plus 1. So as we discussed, we gave 3. So what is the meaning of 3? 3 qubits. So 3 plus 1, 4 qubits. So last qubit dedicated for implementing state 1. Implementing state 1. So next what we do, we try to create a black box. Next what we do, we try to create a black box. So we try to create a black box from the oracle. Okay. So likewise, in the same way, we are creating n plus 1 qubits, n plus 1 qubits along with n classical bits. Okay, we are implementing NOT gate. Then we are implementing Hadamard gate for entire quantum circuit. So this is how you can create multiple Hadamard gate. So for a entire circuit. So this single line will create multiple Hadamard gate. So next what we are doing, we are creating a barrier. So within that barrier, as we discussed earlier, the black box is implemented in middle of your circuit. Then what we are doing, we are creating a barrier once again. Then we are implementing Hadamard gate for range of qubits. Then we are doing measurement for all qubits. Then we try to display the circuit. So if you understand the previous code, you are able to understand this code. I try to run this circuit. So look over here. Look over here. So we implemented Hadamard gate for all qubits. Okay, only for last qubit we implemented NOT gate before that. We implemented NOT gate before that. So try to write over here. So all these are state 0. All these are state 0. Okay, so this is state 1. Then what we are doing, we implemented Hadamard gate for all qubits. Hadamard for all qubits. Okay, so this is your function. This is your function. So what is your function? It is a black box. It is a black box. Okay, we implemented only NOT gate. So sometimes we can implement control NOT gate. Control NOT gate. So in this case, we created only NOT gate. Okay. So after that, what we are doing, we are implementing a series of Hadamard gate. So we are not implementing Hadamard gate for last qubit because this is helper qubit. You can see difference over here. This is helper qubit. So helper qubit doesn't have any second Hadamard gate implementation and any measurement because no purpose. No purpose. Okay. So this will help to react with your function, black box function. So that's all. So this will help to react with your black box function. Okay. So for all remaining qubits, we are doing measurement, a serial measurement. Serial measurement. So likewise, you're able to change your oracle function over here. You can change your oracle function over here. Okay. So depends upon the black box, you can change your function type. All of you able to execute? All of you able to execute? Okay, fine. So next we try to transpile. We try to transpile. So it is like previous code. So no need to explain the each coding step by step. Next we try to implement what type of function it is. So next one is Bazrani Versatile problem. So you can take like a homework. You can take like a homework. So you implement a Dye-Josh algorithm. We implement a Dye-Josh algorithm. Next, we are about to look Groover's algorithm. Groover's algorithm. So before that, I try to cover theory part. I try to cover theory part. Today we're going to cover about Groover's algorithm as soon as possible, theoretical aspects. Then be followed by a demonstration. So Groover's algorithm is the only algorithm created by Indian, recognized all over across the globe for uncertain search. So this is very famous algorithm. So developed by an Indian, Low Groover. Okay. The problem is actually based upon finding needle. The problem is actually based upon finding a needle. So look at this image. We have a big haystack. Okay. Finding a needle in a haystack is very tedious process. So how to identify a needle in this haystack? By scanning each and every haystack part by part. At some point of time, you're able to attract that needle through a strong magnet. So if you are using a strong magnet and if you are scanning part by part, at some point of time, you're able to identify that needle. Okay. In similarly, in classical, if you have n unordered items, okay, if you have n unordered item, if you want to identify, if you want to identify uh, this item, if you want to identify this item, okay. So what is the best possible case you can do is n by 2. So you need to divide your n ordered item into two halves. Okay. If you are searching this n by 2, you're able to identify whether it is existing or not. Okay. If you're able to identify, if you're able to search this n by 2, whether you can say this existed over here or not. So this is the best average case we have n by 2 classically. Okay. So what is the worst case we have? N times. Suppose if your item is existed in the last part, then you need to search all n items. So this is the worst case. This is the worst case. Okay. So you always look at the average case to guarantee the algorithm success rate. So classically, you need to search half of your n ordered items. Okay. In Groover's item, in 1996, he proposed a fast quantum mechanical algorithm called Groover's algorithm, which is based upon database search. Okay. So how many times you need to search your item drastically reduced to root n times. Suppose this is the n number of items. So what is the average case or best case? N by 2 in classical. But in quantum, you need to search only for root n times. Only for root n times. Imagine n equal to 100 items. Okay. So what is the best case for classical? N by 2. It means 50 times you need to search. You need to do 50 search. You need to do 50 search. Okay. But in quantum, root 100, you need to search only 10 times. Only 10 search, if you are doing by using Groover's algorithm, you are able to identify that item. So this is a exponential speed up. So suppose if you have million things, you need to search only for 1000 times. Okay, which reduces drastically. So in quantum, you need to identify the correct answer. So imagine your correct answer is like, I'll select this pointer. Your correct answer is like this yellow area. Okay, but quantum will give a mixed kind of outputs. So it will give correct output, it will give wrong output. So it will have combination of all output possibilities. So orange is the correct answer, but you also get red color, you also get blue color, you also get black, white, and gray color. But what you're supposed to do, you need to increase its correct amplitude. So what is the correct amplitude? This orange color. And what are the wrong answers? Remaining all this color, you need to decrease all our amplitude. So if you are doing simultaneously, at one point of time, your striking rate will become higher. Your striking rate will become higher. So this is the idea of Groover's algorithm. This is the idea of Groover's algorithm. In initial step, you have n number of qubits. You have n number of qubits, and you are creating a black box function. And this function will identify the given items. So what you are doing, you are having n number of qubits, and you are putting in equal superposition. So how you are able to achieve equal superposition? By implementing Hadamard gate. Once you implemented Hadamard gate, you require only 2 power n qubits. 2 power n qubits, half of your input. Okay. So for each and every time, you'll get amplitude for 1 over root n. So this is the basic idea. This is the basic idea. And you need to start to search one by one item. You need to start to search one by one item. Suppose if your item is over here, okay, you need to mark it down. So how will you mark? How will you mark? Your function will return 1 if needle is found. It means your function need to return 1 if the needle is found. If it is not found, it will return 0 for remaining items. So this is how your algorithm works. This is how your algorithm works. So if it identify needle, it will return 1. For remaining, it will return 0. For remaining, it will return 0. Okay. So once you do this, then you can identify the correct answer. Then you need to invert that phase. So what is supposed to do? Once you identify that correct answer, you need to inverse that positive phase to negative phase. So how will you do that? By doing a function flip. So whenever you find the correct answer, you need to do a phase flip. You need to multiply that item with -1 to the power f of x. So this is called alternative function. So note down this function. This is called alternative function. So what this function will do, it will change from positive cycle to negative. Okay. So once again, you multiply it with the same function, it will convert negative to positive. So it will change phase of a particular amplitude. So we run for first time. First time we identify that particular item. Then what we did, we try to invert that phase. We try to invert that phase. We cannot do measurement right now. We cannot do measurement right now. It is not like Dash algorithm or Dash algorithm. We need to run for multiple times. If you do measurement for a single time, it will collapse to any probable possibility state, any random state. So which is very dangerous. Okay. If you're executing Gruber's algorithm for a single time, we cannot believe that answer. We cannot believe that answer. So you should not do measurement right now. You should not do measurement right now because it will consist 1 by root 10 amplitudes. Those many amplitudes will get. So our goal is to amplify the correct answer. Our goal is to amplify the correct answer. So there are two possibilities. You need to increase the amplitude of correct answer. You need to decrease the amplitude of wrong answer. Okay. So how to amplify the correct answer? You need to find average. So you need to find average. So this is your correct answer. This is your correct answer. Amplitude in terms of amplitude. Okay. So all these remaining are wrong answer amplitude. Wrong answer amplitude. So what happens if you able to do average for the whole signal range? For the whole signal range, only the wrong answer amplitude are get affected by doing an average. Okay, correct answer amplitude is never got affected because it is in negative phase. Because it is in negative phase. Okay, so once you do average, okay, after doing average, what you supposed to do? You need to reflip that correct answer to opposite side. By doing that, you can find the difference between the correct answer and wrong answer. Because we did average, then we flip the signal back again, then we can able to see the complete difference. So this is for the first iteration. This is for the first iteration. Okay. Then what you do? Then what you do? You need to repeat for n number of times because the first time if you are doing, it may give wrong answer also. But if you are doing for n number of times, okay, the correct answer amplitude will get the maximum amplitude. The correct answer amplitude will get maximum amplitude. You can see the clear difference between correct answer and wrong answer. So finally, if you are doing measurement, you will get the correct answer output 100%. So this is the theoretical explanation of Gruber's algorithm. This is the theoretical explanation of Gruber's algorithm. So I'll share this link. I'll share this link. So go to this link. Maybe I will go through login. Sometimes it will lead to wrong page. So go to learning. Go to learning. Go to modules. Go to modules. In modules, you have Gruber's algorithm. So only go to this page. If you go for some other pages in Qiskit, you will get confused because the code versions are very different. So go to this link. All of you go to this link. So download this notebook over here. Download this notebook. I hope all of you able to download the notebook. So once you downloaded, upload that file in this QBraid. Upload that file in this QBraid. So if you upload it, it will come in this way. So once you uploaded, what you do, select your kernel, select the Qiskit version, the latest one, what you install. Make sure it is, the coding is working. Make sure the coding is working. So it is working, no error. Working. All of you able to download? So put in the chat box. All of you able to download? Okay. So as we discussed, so this is the classical part. Classical part have two players. So player one, your number of inputs, bin of inputs, and we are having a Oracle function player two, and we got output. Okay. So we need to check multiple options, and which one is correct, we need to amplify. Okay. So your function will return one if you able to find that item. Okay. Otherwise, it will return zero. So this is problem setup. I try to zoom for your convenience. Okay, so within root 10 times, it will identify your item. It will identify the given item. Okay, so first it will create superposition. So first it will create superposition for all possible states. So how it is achieved? By creating a Hadamard gate. So for each and every qubit, you need to create a Hadamard gate. Then you need to repeat this process for each and every time. Then after enough iteration, you need to do measurement. Okay. So this step number one, you need to create superposition, then you need to apply Oracle function, then you need to apply Groover's operator. So Groover's operator are responsible to amplify the mark state. So whenever you find that a correct answer, you need to mark that state. Okay. So this is the mathematical explanation of that Groover's function. Okay. So F is the function you need to create, which will map your binary string to a single binary variable. Okay. So this is like marking. So 0, 1, 0, 1, 0, 1 is like marking. So likewise, you can mark whatever the sequence if you want to define. So this is marked for 6 bit. You can mark for 2 bits. You can mark for 3 bits. So whatever you need to mark, you can mark. Okay. So here the n number of sequence is 6. So likewise, you can increase up to n number of items. Okay. If there is equal number of ones and zero, it means it is equal superposition. So each and everything you need to implement Hadamard gate to implement equal number of strings. Otherwise, you can create uneven numbers. Uneven numbers. So this is the same thing we are repeating in theoretical way. So first we need to prepare the initial superposition. We need to apply Hadamard gate for all qubits. Then we need to mark the targeted state. So once you marked, then you need to do a bit flip, sorry, a phase flip. Okay. After that, we need to do diffusion. We need to do diffusion. Okay. So in diffusion, again, you need to apply the Hadamard gate and a phase flip, apply to all qubits. Then you need to do repetition. So finally, you need to do measurement. So whatever we discussed over there, through image, you can be able to understand. Through image, you able to understand. So what we discussed? What we discussed, we have n number of qubits. We have n number of qubits. So here n equal to 4. Here n equal to 4. Okay. We implemented equal superposition with the help of Hadamard gate. Then function is applied. Okay. We marked that function. Then we applied Hadamard gate. Then a diffusion operator is over there. Then again we apply Hadamard gate. Then we apply equal measurement for all qubits. So we are repeating the same concept. For stage 0, we implemented Hadamard gate. Maybe I'll use pointer. We implemented Hadamard gate over stage 0, which is equal to positive state. So this is the mathematical explanation of positive state. Then we implemented Hadamard gate in state 1, we got negative state. So this is the first step. So next what we are doing, we are applying Hadamard gate. We are applying Hadamard gate for positive state. So the whole bunch is positive state. If we applied Hadamard gate for positive state, it will lead to state 0. So this is for negative state. For negative state, again, if you are applying Hadamard gate, you will get state 1. So I need to remember this property. So all the ways you need to remember. So this is for 2 qubits for your understanding. This is for 2 qubits. So this is psi 0. So it contains state 0, 0. So after Hadamard, you'll get positive state. Okay, psi 1. After your function, you don't know what state it will go. So psi 2 entirely depends upon your function. So you cannot predict this psi 2 if you don't know your function. Okay. So until psi 1, psi 2, you're able to predict your quantum state because this is known to you. But after your function, you cannot predict your quantum state because entirely depends upon your function. So likewise, you need to understand your quantum circuit execution from left to right. Suppose you map this function as state 0, 0. It means it is 0, 0. Then everything is predictable. So psi 1 belongs to this combination. So psi 1 belongs to this combination. So this is also positive. This is also positive. So that is what I told. Maybe I will zoom out a little bit. Even though I cannot go and explain. Okay. Okay, I try to explain over here. Even though it is very small, so you can check your laptop. So this is stage 0, this is stage 0. Okay. So after this, you will get positive state here also. This combined state psi 1 is mentioned over here. So this is positive state and this is positive state. And these two positive state combined in this way. So for psi 2, it depends upon your oracle marking state. So what is the oracle marking state? You got state 0, 0. So you got state 0, 0 means you mark only for this state. So remaining state will get altered. Okay. So this state will get altered. This state will get altered. Only this state remain as it is. So that is why you can see the negative flip. Are you able to see? That is why you got negative flip. So once you got negative flip, able to know it is not correct output. It is not correct output. So likewise, you need to change phase of all remaining states. So what is your correct state? 0, 0. So what is your correct state? 0, 0. For remaining combination, you need to change sign. So in psi 2, you changed. Okay, like in psi 3, you changed for remaining state. Are able to see the state change in 1, 1. Okay. Also for 1, 0. Also for 1, 0. So only state 0, 0 is not get affected. So go through this equation one by one and try to understand how the encoding is happening. How the encoding is happening. So after psi 5, definitely you'll get state 0, 0. So that is the idea. So here we marked state 0, 0. So this is the item we need to identify. We started from state 0, 0. But over here, you have 4 combinations. Over here, you have 4 combinations. State 0, 0, state 0, 1, state 1, 0, and state 1, 1. State 1, 1. So we are eliminating remaining state over here. We are eliminating remaining all 3 states over here. So because of this operation, all these 3 states got eliminated. So finally, we got state 0, 0 from your circuit. So state 0, 0 is what the item you're looking for. What the item you're looking for. Suppose if your item is state 1, 0, then you need to do all this process ever for 1, 0. So you need to design all this function to eliminate 0, 0, okay, then 0, 1, then 1, 1. So this is the idea of Groover's algorithm. So we try to execute this code one by one, part by part. All these are theory, no need to execute. All these are theory. I try to copy this code, try to explain. Okay, so this code importing the relevant packages, Groover operator, MC, MT gate, Z gate. Z gate is responsible for phase flip. Okay, and it will visualize plot distribution. It will do transpilation. So all these packages are relevant for our operation. So we try to run this code. It is executed without any error. So check from your side. Then what we are doing, step number 1, map classical input, map classical input to a quantum problem, to a quantum problem. So this MCMT gate will help you to implement multiple Z gates for all wrong outputs. So according to your marked state, you need to implement. So what is the marked state? 0, 1, 1. 0, 1, 1. So you need to implement phase flip for 0, 1, 1 because that is your correct answer. For remaining, you need to implement as it is. So 0, 1, 1 is your correct answer. That is why you are doing a phase flip. So we implemented a quantum circuit which consists 3 number of qubits. Okay, and we are implementing MCMT gate which comprises multiple gates. Okay, so all these gates implemented Z. So it implemented Z gate. Okay, for remaining 3 inputs. So 3 minus 1 comma 1. I hope all of you able to run this code. So once you marked, what you can do, you can go for Grover's oracle. So you need to mark your quantum state. You need to mark your quantum state. So according to your input, it will replace your input over here marked state from the list. So 3 qubit means it will contain 8 possible combinations. So out of 8, you need to mark only 1. You need to mark only 1. So it will create n number of qubits. If you are giving 3, it will create 3 qubit system. And it will mark only the given target. Remaining all, it will do a bit flip. So try to run this next code. Try to run this next code. So no error. No error means executed successfully. So always go to view, enable show line numbers. If there is any error, it is easy to identify. So go line by line. So they gave ample amount of commands. You can understand what that code is meant to be. So once you understand the theory part, compare the theory with your coding part. So only it will flip the targeted pattern. Okay. Remaining it will remain as it is. So it will implement for 0. So MCMT gate is multi-control gate. So multi-control gate. So it will implement NOT gate for all zeros. Okay. For only one combination, it will implement MCMC gate. Again, it will implement a NOT gate. So initially one NOT gate, in between this combination of MCMC gate, then again one NOT gate. This is the marked state. So what is the marked state? 1, 1, 1, 0. So for that, we created a Grover's oracle. Okay. So this is your actual input. So according to input, your oracle function will differ. So here what I do, I try to copy this line. I try to copy this line. I'll paste. I try to change this combination. I try to change this combination. So suppose if I implement 0, 0, 0. So like this, I got different oracle function. So this is how you can change your marked state and you'll get the different oracle function. So try to change for 1, 1, 1. So according to that, it will modify the remaining states. So it is not allowed. Okay. So we are implementing for only 3 qubits. Okay. So the last one always for reference. So try to change for 101. You'll get different oracle function. So oracle function entirely depends upon what is the marked state you possessed before. So if you are running any algorithm, you need to modify code, then only you are able to understand how it is working. Next, what we are doing, we are calling Groover's operator from the oracle we built. So this is an example. This is an example for what we created so far. So each time if you call, it will create according to your previous circuit. So here you can see multiple control NOT gates, multiple control Z gates. So these are multiple gates. Okay. So most probably you never came across. So please go through tutorial I already shared. So yesterday I covered multiple control NOT gate. Today I covered multiple control Z gate. So remaining gate you are familiar. I hope so. This is a NOT gate. This is Adamat gate. Okay, remaining everything same. So you need to run for multiple times. You need to run for multiple times. So how many times you need to run? It will tell you. So 3 times you need to run. 3 times you need to run. So if you are increasing number of qubits, okay, you will get optimal iteration is supposed to do. It will print out. So this is very crucial. This is very crucial. So instead of 9 combination, instead of doing 9 iteration, we are doing only 3. Are you able to get the idea? So what is the number of given input? 3 qubits. So 3 qubit means you have 9 combinations. So out of 9, you need to run for only 3 times. So root 10 times. So here n equal to 9. So if you run less than 2, you cannot get the correct output. You cannot guarantee. So note down this point. If you run less than this optimal number of iteration, you cannot get the right output. Your output is not guaranteed to be correct one. So as we discussed, so we have 3 qubits with one additional qubit. Then we have 4 Hadamard gate. Then we have 3 functions, a Groover functions. So one is get started with marking, one is get started with diffusion, the another one is get diffusion. So finally you'll get the correct output. The same problem you can run by using your quantum hardware. Here I try to run. I submit a job, it will take some time. Now I got IBM FEZ. So each and every time it will change, right? So go and check my library. Go and check my library. So click here, go to compute resource. It is not having Ansela qubit because we need to run for multiple times. So automatically IBM physics got selected for me. So in previous we selected IBM Torino. explicitly. So here it selected IBM FIS. If you are not getting this output, it means you are not able to get quantum system. So we asked the IBM server which server is least busy. So according to that, we are able to get the backend. So automatically IBM FIS is allocated for us. Now we are running that circuit. We try to do transpilation. So if there is any error, it will show. For me, there is no error. Then this is one important point. Okay, you need to identify total number of depth in your circuit. Total number of depth is 425. The total number of depth for 2 qubit gates is 111, which is huge number. Okay, I'll show that circuit for your reference. So go to your account. Once you're able to submit your job, you can see over there. So this is the latest job what I submitted. No, you all. IBM FIS I use. Okay. Okay, I never executed, right? I never executed. Now I going to execute. So I am executing for 10,000 times. I'm executing for 10,000 times. Now it is submitted. It is getting executed. Now go to your account and check. Now I submitted my job. Now it is in pending status. Now it is in pending status. So this is the circuit you generated. So look at over here. So these four are selected qubits. But if you do transpile, it will go for multiple qubits. So it will take only 4 seconds in quantum processing unit. You can check from your backend how much time it will take. So this is the estimated time. I need to wait for some time because yesterday what I did, I submitted a job. It took 2 hours to execute. 27, 26. Yesterday I submitted, right? Yesterday it nearly took 1 hour. 1 hour. Now you can see the whole circuit, how it is transmitted. So this is about the depth. Your simple circuit is converted into this much level automatically by during transpilation time. Okay. Suppose if you don't have access to real quantum system, you can run in local simulator. I try to do this. So just enable sampler. Just enable sampler. Then result. Then distribution. So this is the probability distribution. Because I need to do proper simulation, I selected hardware sometimes, I selected simulator sometimes. Okay, because it is pending, I am not able to execute, but you can run this. You can run this. So before step number 4, okay, in this cell, just enable this line number 3, 4, and 5, and you will get the output. If anybody got output, please put in the chat box. If anybody got output, put in the chat box. Okay, in the same way, able to get the output. In the same way, able to get the output. So output will appear in this way. Output will appear in this way. Because we marked 110, so that is why we got highest amplitude. So previously, go to previously. So what we marked? We marked 1110. So here we marked, right, 1110. So that is why we got highest amplitude for 1110. Because we have 4 qubits, we have 16 combination. Because we have 4 qubits, we have 16 combination. Out of 16 combination, we got the highest amplitude for 1110. Try to reduce number of qubits. You can give a marking list, so better you can able to understand. So start with a small number, then gradually increase. Okay, use the same code, differentiate number of qubits, differentiate mark state, and observe how the states are get changed. Yes, exactly, exactly. Very good. If you're able to get output, at least one person, that is very good for this workshop. So I tried to introduce one more simulator called Penny Lane. So if you're interested in quantum machine learning, you can go to this tool. Okay. So in this tool, you can find so many resources. You can get quantum data set. So normally in IBM also, they didn't upload this many quantum data set. Okay. So you can visit this website. You can have a quantum data set. Regular probability is just like classical probability. Quasi probability involved with the density matrix. It is like all combination in between quantum states. So like superposition, it contains all possible uh, states. Okay. So here you can go and install Penny Lane. If you want to install, you can go like Google Colab. You can follow these steps. For each and every operating system, they mention how to install. Okay, for Linux, for Windows, for Mac, they gave platform wise. Okay, package wise. Right. So in KubeRide also, you able to select the environment. You able to select the environment. and you need to add kernel for penny lane. I shared penny lane over here, I think so. Yeah, here I have already have. I shared in the chat box, I think so. What is the link you are asking? Okay. So I'll stop at here. I will stop at here. If you have any doubt, you can ask me. We already discussed penny lane in previous series, FDP series. So you can go and check over that. In the upcoming session, they will discuss about CDAC tool called Qniverse. This is also similar to IBM Qiskit. So once you are familiar with IBM Qiskit, learning other quantum platform, other quantum simulator is very, very easy for you, become easy for you. So thank you all for listening to this wonderful FDP. Suppose if you have any doubt in further, if you need any help, you can contact me. I'll share my social media ID. Thank you.
Thank you, sir. Thank you so much, sir, for the wonderful session on simulation using Qiskit and Penland platform. And just an announcement to all the participants. Quiz 3 is going to be scheduled today and it will be available till Monday midnight. So please complete the quiz before time. So that you do not have to send emails or requests to for further extension, right? So Monday midnight will be the deadline for quiz 3. Thank you, Jaykumar sir. Thank you so much for
Thank
this
you, sir.
wonderful.
Thank you. Thank you.
Hope
Thank you.
we will meet again in the upcoming FDPs or the sessions.
I can understand for some participants, simulation is little tough because involved with more and more code, but they gave free template for you. So if you have any students related to CS and IT or faculty, if you have friends, please sit with them, try to run all these codes. Very easy for you. So if you feel it is difficult for you.
Yes, non-CS participants can take help from CS faculties. Yes. Thank you, sir. Thank you so much. Once again, quiz 3 will be scheduled today and it will be available till Monday midnight. I think.